Hello, good evening, everyone. My name is Scott Grizzard from the University of South Florida. This is Calculus 1. This is the fall 2020. And tonight we're going to be talking about L'Hopital's rule. So last time was the mean value theorem. Now in the book, L'Hopital's rule comes before the mean value theorem. But to prove L'Hopital's rule in the full version, you have to have mean value theorem. And the proof is in the back of the book because they don't want to prove it at the same time. And we're not going to do the full proof, but I want to kind of mention that it's dependent upon it and kind of show you the trick that the proof is using in an intuitive sense. And then if you want to see the proof, it is in the back, and you can read it for yourself. So the last two lectures have been very theoretical high. Now we're going to get more back into the computing of the things. And I've talked about L'Hopital's rule before. So recall this idea, right? So recall this kind of diet version of L'Hopital that we did when we did the linearization. So I had this idea that I had this idea that I could take the ratio of the linearizations, and the problem that I had from the beginning was this kind of recall. Oops, that's a weird color. So recall from linearizations that I had this thing from linearization. I wanted to compute the limit as x went to pi of sine 2 pi over 4x squared. I'm sorry, that's sine 2 pi, sine of 2x over 4x squared minus 4 pi squared. Okay. So what I did was I had this thing that I called Diet L'Hopital's rule. And it was very heavily dependent upon the fact that both f of a and g of a went to 0. But it had a couple conditions here, right? F needed to be differentiable at a. If f, so I had this if f is differentiable at a. At a, g is differentiable at a. And then this thing where g prime of a did not equal 0. Then the limit as x went to a of f of x over g of x equaled f prime of a over g prime of a. All right, so how do we feel about that 1 to 5? This was the old Diet L'Hopital's rule. How do we feel about that? 1 to 5. Do I have a 1 to 5er here? Okay. Let's see. There it is. Okay. And I'm way too far from the microphone, so it's probably not picking up my voice. Okay, so, and there was a proof for this. I'll do it in just a moment. I did it in the notes. I'm not sure if I did it in class or not. Probably not. So what I do, right, I know that this goes to 0, right, because this whole thing is that. And when I sub in 4 pi squared, I know that this is going to go to, so this right here, let me just pull this down so you can see it here. So I've got a little room to write. So I had this idea that this piece here would go to sine of 2 pi, which equaled 0. And I had this idea that this bit would go to 4 pi squared minus 4 pi squared, which equals 0. So I had 0 over 0. And I could apply L'Hopital's rule by just taking the derivative of the top and the derivative of the bottom. And by the way, this h is just universal. Okay? So what I did was I did d over dx at x equals a of sine of 2x. And then I did the same thing on the bottom. D over dx at x equals a of 4x squared minus 4 pi squared. And then I'd wind up here with the derivative of the top, which was cosine of 2x times 2. I'm skipping steps here on the chain rule because you can go back and watch all the steps on that video and in those notes if you desire. And this one here was 8x minus 0 on the bottom. And remember, I want to evaluate both of these at x equals pi. So what I get is I get cosine of 2 pi times 2 over 8 pi minus 0. And that gives me this, this should be diet L'Hopital, by the way, diet. And that gave me here, I would wind up with 1, 2, so I wind up with 2 over 8 pi, which equals 1 over 4 pi. So how do we feel about that 1 to 5? Okay. Well, the proof of this, the proof of the diet version is actually kind of what I do. I don't exactly use the linearization. What I do is I work backwards and I use the definition of these things. Okay. So what I do is I kind of just go, okay, so the proof of this and the strategy for the diet version is to work backwards. So for the diet version, the proof looks like this. I'm going to go f prime of a over g prime of a equals, okay, this is the limit as x goes to a of f of x minus f of a all over x minus a. This right here on the bottom is the limit as x goes to a, g of x minus g of a, all over x minus a. And then what I've done, once I've done that, I actually am in pretty good shape. So what's going to happen here? I mean, you can already see what's going to happen. This right here is going to go to 0. First, the quotient law says that this ratio of limits is the limit. And the reason why that works is because, so the quotient law for limits, and the reason why this works is just g prime of a doesn't equal 0. So both of these limits exist, right? They're both the definitions of the derivative, so I can combine them using the quotient law. We usually use the quotient law to go the other direction, but I can go forward. I can do this. Normally we use it to go the other way, but I can use it to kind of just go this way instead. And what I'm going to do is I'm going to take this x minus a and move it to the top of the bottom, and move this x minus a to the bottom of the, to the top of the top. So what I'm going to wind up with here, Yeah, so this goes to the top of the bottom, and this, when I take the reciprocal, multiply by the reciprocal, it's going to wind up there. So I wind up with g of x here, minus g of a on the bottom, and then I wind up with x minus a and over x minus a. Yes. Now, once I do that, these things both go to 0. These things are both 0. And since these things are both 0, they just go away, right? So this becomes limit. This right here is 0. And this right here is 0 from the hypothesis, right? So my hypothesis was that... Oh, and I didn't write that condition. Oops. Note to self, I need to fix this. Sorry, I forgot to write that they were both... That's kind of the whole point. Advantage of doing this. With this thing, I could just... Oops, I don't want to do that. I could just go in and add that 0, that real fast. Here I had g of a equals 0, and I had f of a equals 0, right? I've got 0 over 0. I forgot to say that. Okay, so now, kind of the whole point. You can only do it when you got 0 over 0. So now I've got x here. This was 0 and that was 0. So I wind up with f of x over g of x, and these two things cancel. So that thing becomes 1, and I'm left with what I wanted. So the trick was just to work backwards. 1 to 5, how do we feel about this little idea, this little proof? This little proof. So this is the proof for the diet version. And I should say that. This is the proof for the diet. All right, this is not the full-blown version. Okay. But what we want... So here's the question. Suppose I had the following situation. Suppose I had a situation where I needed it twice. Okay, so let's look at the following problem instead. Okay, no one's voting. I hope that you're all out voting for, elections and things, but no one's voting here, and that's making me sad. Go vote. Okay. So suppose I have the following problem instead. Let me just pull it up. I wrote it here somewhere to make sure I had it. Yep. Let's look at this problem. The limit as x goes to 0 of sine squared x over x squared. All right. Here, there's the problem. This goes to 0, and this goes to 0. But the derivative of x squared, when x equals, right, so I'll just call this g. but g prime of 0 equals, x2 times 0 equals 0. Can I do something about this? So I've got a requirement here that g prime of a not equal 0. And I need the derivatives of the other two to exist. So do we see why this is a problem for the diet version? Okay, are there any questions about that? Why I have a problem with the diet version? The diet version cannot help me yet. All right. We need a new theorem. And the new theorem is the big boy version. Okay. So this is the 0, full-bodied version of, right? No more light beer. We're going for the full-bodied beer, right? This is the IPA version, not the wussy one, too. We're going full hop on this sucker. All right. So this right here is the full-bodied version, full version of L'Hopital rule. And there's two theorems that are L'Hopital's rule, by the way. There's the 0 over 0, and then there's an infinity over an infinity. They are actually two separate things. The book calls them one theorem, but they're two theorems. They're different. Okay, so don't... that's kind of nitpicking, I suppose. But if you think of them as two theorems, you won't make one of the big common mistakes. So that's why I wanted to say that. Full-bodied, L'Hopital's rule. Of course, he's French, so he's probably insulted that I'm talking about him and beer and the same thing. Oh, you should be talking about wine. L'Hopital's rule. And this is the 0 over 0 version. Okay. Now, some things have to be a little bit different. So I've got a bunch of conditions that are kind of like, and nobody ever mentions them, but they're there. And then I've got conditions that I have to make sure I mention. All right. So what I want to do is I want to take the derivative of something that is the limit as something like f of x over g of x. So let f and g... let's do a first. Let a... This is kind of the conditions. Let a be in... This is going to really freak you out. What is that? What is that? I have hard endpoints on the infinity. You can't do that. I can. What am I saying? I'm saying let a be either a real number or one of the two infinities. Negative infinity, positive infinity. You can't have negative infinity and positive infinity be the endpoints. So what I mean by this is a can be any real number or one of the infinities. Let a in R or a equal plus or minus infinity. Does that make you happier? I hope that's not the only thing you get from this lecture. And then what I want is I want let f and g be defined near a. Now, I'm going to use this near a stuff a lot. So just a reminder, So when I say near A, I mean that, right, I've got right near A and I've got left near A, but neither of those include A itself. Now, it could happen on A, but I'm not requiring it to be on A, but not required at A itself. Right, so I've got some interval, and remember I used delta for this. I've got it so true at A minus delta comma A union A plus delta, right? For some delta, right? It goes on here in the X space. Here's A, and it goes on here and here for some little insignificant little piece. Okay, so 1 to 5, how do we feel about that near A business? Because I'm about to do a lot of it. Right, so, I've got A minus delta and A plus delta. It's true for something around A, but I don't actually care about A. All right, and that's somewhat important for this, because this is going to let me go after derivatives where the derivative itself at A itself is not defined, but it's defined everywhere close to it. Okay, so these are my kind of the conditions that, I've got a bunch of these, so I'm going to require a little bit more than I did before. Before, I only needed this to be differentiable at A itself. Now I need it to be differentiable in a neighborhood near A. Not at A. I'm not requiring it to be differentiable at that point. But that's going to mean I'm going to need intervals on both sides where it is. Okay? So that's going to be part of one of these conditions. If f is differentiable near A. I'm going to write F and G. I don't feel like writing all these terms twice, because they both have to be. If F and G, and now I need an R, right, because this is English, are differentiable near A, and this is weird. F prime has to be continuous, and so does G prime. Okay. Sorry, are continuous, not differentiable. Continuous. So I can't have any jumps in my derivative. Okay. What else do I need? Those are the big two things. And then I need G not to be a constant function. All right, so it can't be 0 everywhere near A. Matter of fact, I need G of X. I need G prime of X not equals 0 near A. But I'm okay at A. G of X, G prime of X can be 0 at A. I just can't have something that's flat. Okay, I can't have everything on the bottom, right? I can't have something on the bottom that is just flat. I need it to not be constant on the bottom, and I need it to not be one of these weird things where every neighborhood has a place where it's 0. But I'm kind of already dishing the weird stuff when I'm demanding the F prime and G prime be continuous. So I just need it to not be the 0 function near A. Okay. I need a couple of other conditions. I need the limit as x goes to A of f of x equaling 0, and the limit as x goes to A of g of x equals 0. Now, the reason why those are in dark purple is those are the ones that you're required to write. These conditions exist. along with the preamble, but you never need to write them. Okay, that just kind of, we assume that that's how it works. All right, and I don't even think the book mentions one of these until it does the proof. And then it's like, oh, by the way, this had to be true. But it definitely mentions those two things. Then the limit as x goes to a of f of x over g of x equals the limit as x goes to a of f prime of x over g prime of x. Now, the advantage of this, right? Well, why? You added all these weird conditions. Why would you say this is better, right? Before, I just needed g of a, and I just needed f of a, and I needed g prime of a to not be 0. And I needed them differentiable at those points, right? But now, I'm okay with it not being differentiable at a, and I'm okay with g prime of a being 0, as long as the stuff near it, on either side of it, as long as the stuff on either side of it, as long as the stuff near it is not 0. 1 to 5, how do we feel about this? Here, I was talking about at. Now I'm talking about near. You could even call this the near L'Hopital's rule, as opposed to the at L'Hopital's rule. So 1 to 5, how do we feel about that? Okay. Now, the intuition for the proof is like this. I'm not going to do the full proof. Now, matter of fact, let's apply it first, and then I'll talk about the intuition of the proof. Okay? So let's do this first. Let's have a little fun with this. So let's go back to our example. All right, our example was sine squared x over x squared. So now what I'm going to do, first of all, I'm going to sub in right, so now I've got 0 over 0. So I'm going to apply L'Hopital's rule, the full-bodied version. And what I'm going to get is this equals the limit as x goes to 0. Notice here, for the regular version, I didn't put that limit sign. I mean, for the diet version, there was no limit sign there. I didn't need it. It's the full-bodied version that needs a limit sign, right? Because I'm no longer going to have this weird evaluation thing either. So the limit as x goes to 0 of d over dx of sine squared of x over d over dx of x squared. Now, what I do is I evaluate the derivatives. This has got a chain rule in it. So the derivative here, I'll even do some of this work over to the side here. D over dx of sine squared x. Remember, this is actually sine of x squared. The squaring is done last. So I've got a chain, and I've got the u is the sine. Remember, this is actually, this notation's a pain in the neck, right? This is actually sine of x squared. So the u in the middle is the sine of x. It's notation. We were talking about this the other day, right? Irregular. The reason why sine and cosine are so weird, and why you have 1 over cosine have a special name called secant, it's because, like, in a language, the oldest terms in the language that stay in the language are irregular, right? So in every language, the verb to be is going to be irregular. You know, we're going to go study Swahili today. Yeah, the verb to be, it's going to be irregular. French, verb to be, it's irregular, right? It's one of those things that it always accumulates junk because it's really old and you keep using it all the time. Sine is like that. And cosine is like that. The reason why it's got all this junky notation that's different than the notation for everything else is because this stuff is 2,500 years old. So you can blame Euclid. Anyway, so what I'm going to have is d over du of u squared times d over dx of u equals 2u. That's probably more than you wanted to know about linguistics in your life. Sine of x, and that is going to equal 2u was sine of x times cosine of x. So on top, I'm going to have the limit. Notice I have to keep that limit of sign around of 2 sine x cosine x all over 2x. So how do we feel about that 1 to 5? I don't want to do that. I'm just going to kind of write that over there. All right, well, now I'm going to have 0 again. Let's change some of these colors here. Well, no, I need to leave it because it's required. This right here, I sub in, I get 2 times 0, and I get 0. This part here, I sub in, I get 2 times sine 0 times cosine 0, which is 2 times 0 times 1, which equals 0. So I've still got things that I can't deal with. But here you can actually see, right? I've got 0 over 0. But now I just apply it recursively. So now I just go again. And you can already see that this is going to do it for me because the bottom is now going to be 2 when I'm done. Right? Now, I've got a product rule here on the top. That's nice. The top is going to be 2 sine of x. Oh, derivative of the first. Let me do it in order. Cosine of x, cosine of x. Yes, I'm skipping steps. You can yell at me. Plus, okay, the derivative of the second times the first here. So this is going to be 2 sine of x times negative sine of x all over 2. And I'm just going to simplify that because when I sub in, it'll make my life happy. 2 cosine squared of x minus sine squared of x. And if you write cosine 2x here, the grader's going to come and hunt you down. I'm just telling you. Don't do it. Right? Don't go, oh, that's the double angle formula. No. And there should be that. I factored out the 2 as well. And the reason I did that is because I wanted to cancel those 2's, and I wind up with this. Okay. Again, if you write cosine 2x there, we're going to like hunt you down and go boom, boom, boom. Why would you do that? No need to do that. Now, I'm going to sub in 0 here. And here when I sub in 0, This bit is going to go to 1. This bit is going to go to 0. And that is going to make me so happy, right? So I do the direct sub, and I wind up with cosine squared of 0 minus sine squared of 0. And that bit equals 1 minus 0. And that equals 1 this week. So how do we feel about that 1 to 5? I just applied it twice. Okay. Couple little things here. Notice I don't use the quotient rule here, right? I evaluate this as the derivative of the top over the derivative of the bottom. I don't take the derivative of the whole thing. I take the derivative of the top and the derivative of the bottom separately. Okay? So make sure you're doing that. Yeah, it's not really a warning thing, is it? Tip. It's a commie tip. If you're tempted to use the quotient rule, you're probably doing it wrong. Not always. I mean, sometimes these things can't have quotients. You're right. The bottom could have had a quotient in it, but you know, you don't need to. You shouldn't be using the quotient rule on every single one of these, right? Let's just gotta say you're taking the derivatives separately. Okay, that's important. You're not taking the derivative of the whole thing. You're taking the derivative of the top and the derivative of the bottom. Okay. All right, so let's talk about briefly the idea of the proof. Because the idea is kind of cool. So what I'm going to do is so the idea of the proof is what I'm going to do is I'm going to take the ratios I'm going to work backwards, and I'm going to take the ratios of the secant lines. Okay? And then what I have, right? So what I'm doing, and so the first part of it is kind of this, this ratio of the secant lines, right? M, F, A, B over M, F, and it's not, by the way, B, and it's not, by the way, that. It's X. So the idea of the proof is this. First, X is your right endpoint. Okay? That's the first weird thing. So what I'm doing here is let's talk about, this should be a G. So this idea that I've got X as my endpoint. Here's A, and I'm talking about the limit to the right. So instead of there's some B over here, but I don't care about the B. The X is the other hard endpoint. Okay? So I've expanded G, and there's some details. That's why I don't want to do the proof. There are all these little details that you have to watch out. But the idea is that I've expanded this, and then I've got the secant line here. We'll do the secant line of F for the moment. And it's the secant line, and it can't be of X because I'm using X. So it's like the secant line of T. Okay? And what I'm doing, if you zoom out here, what I'm really doing is I'm using the mean value theorem to turn this into a kind of like a polygon. Okay, so instead of having this thing here, I'm going to use the mean value theorem to turn this thing into a polygon, essentially. So here's some, I don't really care what this is, I'll call it B. This is like an X here, and this is a hard endpoint. And then I'm using the mean value theorem in a sense to turn this bottom part into a polygon. Let me do this in a different color. Because remember, I don't want to mention f prime of a. Right? I don't want to mention f prime of a. This is to avoid mentioning f prime of a. So what I've got is I've got that the limit as x goes to a. I'm going to wind up doing a whole bunch of things, but this is the idea. I've got the secant lines, the ratio of the secant lines. And notice that x is this endpoint. How do you feel about what I've just said? This idea that what I've got is mfa of x equals ma and over mg ax. Okay, so I have this ratio of these secants, of the slope of these secants. Okay, and that's weird. But the idea here is what I'm turning this into is a polynomial, is a polygon of some sort. Right? Instead of having this curve going on, I want an edge. Okay? And then what I'm going to do is I'm going to use the mean value theorem to say there's some u where this is true. There's some u between x and every a. There is some u depending on x. So that this slope and this thing's derivative are the same. So I've got ux equals the minimum of u such that f prime of u equals mf ax. So that's the intuition. I'm picking up this u for every x, and then I'm taking a limit. So as I slide x this way, okay, as I slide x toward a, this ux gets closer and closer to a. So what I get is, I should not be using red for all this because this isn't, a red thing. Right? So as I slide x to a from the right, ux goes to a, and I have the limit as x goes to a of f prime. Remember, f prime of u equals ma, this thing. So I've got the limit here as x goes to a of f prime of x. Equaling the limit as x goes to a of f of x, right, through the min. And I should say that this is both. g of x. Based on this idea that what I did was made a polygon and then slide. How do we feel about that? I'm just trying to kind of explain that there's some little trick that they're doing here. I'm not really sure if it's really a good notes thing, right? It doesn't exactly what the intuition that I'm trying to explain here. It needs more. It needs animations. I need to like go get the computer and animate this trick thing. But that's the idea in kind of broad strokes. That I take the ratio of these secant lines and then I do some little sliding with the MVT. And as I said, if you want the proof, you could see it in the back. But I kind of wanted to get this idea across because we'll be using a simpler version of this idea when we do the fundamental theorem of calculus proof. All right. So I should write. You can ignore not on test, but you should see. Because this trick is coming back. Right, so it's not that and there it is kind of required thing. So I don't want you to like spend time worrying about this now, but I do want you to kind of watch the video and kind of see the kind of idea of sliding because this trick is going to come back again. It'll be a simpler version of the trick, and I'll explain it in much more detail, and we'll actually do all the little details. Okay. So what we had now, I just wanted to kind of do a little aside on that because it will come back. This idea of using the MVT to polygon something is coming back. All right, so we have a second version of this. And this is the infinity over infinity version. Okay? And here's what it says. Basically, everything that this thing said before. What does the infinity over infinity version say? Well, I'll show you. I just do this. I'm going to put this right here. We'll get rid of you. And the only thing that changes if blah 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 if that's it. Same theorem, same everything. And if you want to prove this from the other version, what you do is you work backwards to prove it. And I do it with 1 over g of x over 1 over f of x, and use 0 over 0 version. So basically what I do is I put the g, 1 over g on top, 1 over f on the bottom. I use the reciprocal rule, and then but I have to do it backwards. Okay, so you do it backwards, and then you just use the reciprocal rule, you're fine. The details are in the book if you care, but that's why it works. But it's important to note that it doesn't mix. So let's look at an example of this. Let's do x goes to, I don't know, somebody, x goes to infinity. Why not? Infinity of e to the x over x. Why not? E to the x over x. Okay, well, this bit goes to infinity. This bit goes to e to the infinity, which equals infinity. So I apply L'Hopital's rule. Now, note these are separate theorems, but I've only got one h. And I do the limit as x goes to infinity of I take the derivative of the top and the derivative of the bottom. So this is the derivative with respect to x of e to the x. And I do the derivative with respect to x of x. And I get the limit as x goes to infinity of e to the x over 1, because e to the x is its own derivative, and that's just infinity. 1 to 5, how do we feel about this one? How do we feel about infinity over infinity for L'Hopital's rule? Am I skipping? It says I'm skipping. I don't know. Okay. And of course, I could have multiple versions, so we could do a second example. So I've got the limit as x goes to infinity of e to the x over x squared. This goes to infinity. This goes to infinity. Equals, with L'Hopital's rule, the limit as x goes to infinity of e to the x over 2x. This goes to infinity. This goes to infinity. Equals, I take L'Hopital's rule. Let's take the derivatives again. X goes to infinity. E to the x over 2. This goes to infinity. This goes to 2. That's not a problem. Okay. So that one I could apply twice. Any questions about that? All right. There's a couple things I need to make sure that I absolutely do not mix these. Okay? So this is a big warning. Do not mix the two theorems. They are separate. Okay? Now, what do I mean by that? I'm looking for I had a good example that I'd actually spent some time on, and I wanted to use it. And now I can't find it. And not just the way. I had a great example. I wrote it all up. It was all nice. It was all neat. It was all perfect. And now I can't find it. Maybe this is it. Nope, that is not it. That's just doodles. Okay, well, I can't find my beautiful example. This is what I get for This is what I get for doing things more than just 30 minutes ahead of time, right? Because if I had done it exactly 30 minutes ahead of time, I would have made sure I had it. This is what I get for being prepared, for working it out in advance. I wasn't prepared because now I can't find the example. Did I put it over here anywhere? Nope. Okay, so we'll do this one. Don't mix and match. They're separate things. So let's say I've got the limit. Oh, let's do something that goes to infinity at the top. So let's say I have the limit as x goes to 0 plus of ln of x over x. Okay? Now, this piece goes to infinity, negative infinity. This piece, however, goes to 0 plus. No L'Hopital's rule. Negative infinity over 0 plus is not LH. Okay? LH is only 0 over 0 or infinity over infinity. They are two separate theorems. I've got a 0 version and an infinity version. 1 to 5, how do we feel about that? I have two separate theorems. I have one for infinity and one for 0. And if I've got infinity over infinity, I've got negative infinity over 0, that's not L'Hopital. Negative infinity over 0 plus, that's negative infinity. Right? I'm shooting off to negative infinity. There's no ambiguity here. Right? The thing on the top is hugely negative. The thing on the bottom is going to little bit of numbers. That's negative infinity. All right, negative infinity over 0 plus equals negative infinity. Negative infinity over 0 minus equals positive infinity. 0 infinity over 0 plus equals infinity. Infinity over 0 minus equals negative infinity. Infinity over 0 does not exist if it's going off to two different things. Right, so just keep this in mind here, that if I get things that are really big on top of things that are really small, that's defined. Let's see, 0 over infinity, if the denominator is getting really big, 0. 0 over negative infinity, also 0. Okay? No L'Hopital rule here. I don't care if you have to memorize these. If you have the picture of 1 over x in your head, you can actually kind of see what's going on. But if that intuition doesn't work for you, memorize them. I think different people think differently. For me, I just keep this little function in mind, right? When I get really, really small, right? When I get really, really tiny here, and I get really, really big on top, I'm going to shoot off, to negative infinity here. I just keep this in mind. But if you don't like that and you prefer just to memorize it, memorize it. But these are not L'Hopital. Okay, 1 to 5. How do we feel about that stuff? I got a question coming. I love it. Finally, a question. Question. Bring me a question. Yes. Oh, okay. So why did I apply it twice in the previous example? I applied it twice because I had infinity over infinity. And then I had, when I did it, when I took the derivative of the top and the bottom, I then got infinity over infinity again. And then once I got that, I got infinity over 2. It's hard to see because e to the x is its own derivative. Let's do a different one. Let's do d over dx. I'm sorry, not d over dx. Let's do the limit as x goes to infinity of e to the 2x over x squared. Okay, so this will make it a little bit more clear because now I'll have a chain rule to pop another 2 off on top. Okay, so now I take the derivative of the top and the derivative of the bottom, and I wind up with 2e to the 2x. Because of the chain rule, I have to take the derivative of that over 2x. And then this goes to infinity, and this goes to infinity. So I go again. And I get the limit as h there, h there. I get the limit as x goes to infinity of 4e to the 2x over 2. And now this goes to 2. And this goes off to infinity, and that's fine. I can do that. Does that answer your question? So I wound up with infinity over infinity. I can go again and again and again. Yeah. Now, you have to be careful because you can get stuck. All right? So if I wind up getting stuck, right, I need to do something else. So I can wind up with, let's say I had the square root. Okay? So if I get stuck, you can get stuck. So warning, you can get stuck, and then you have to do tricky things. Okay, so let me show you one of those. Okay, so let's do one where you'll get stuck. So let's do the limit as x goes to infinity. Actually, that one won't go to 0 of let's see, something that will go to 0 on the bottom. Let's do this. Let's do x squared. I don't want an x squared. I want the square root of x plus 1 over the square root of x plus 1. No, that one won't go to 0 either. That one would go to 1 over 1. That'd be fine. I should have worked out an example for this. To the right, that would be ln. Something that would go to square roots always work nicely. Let's do square root of 1 over x and ln of x. No, because if I take the derivative, that'll work. Something that else that goes to infinity. Let's do infinity, and let's do the square root of x e to the x. I think this one will give me something bad. Okay, I've got to come up with another example. I'll come up with one and I'll come up with one and I'll do it later. Right, so sine of x as it goes to 0. But then when I want one where I take the derivative and I make my life unhappy. So what is one where I keep taking the derivative and my life gets less and less and less and less happy? Right, so e to the x as x goes to 0. So it's got to be something with infinity. And then on the bottom, I need something that will keep going to infinity forever. So it's so e to the x as it goes to 0 is just going to go to 1. So I need something so that you can have things that just make your life unhappy. And I don't want to spend too much time thinking about it. But you can, let's see, if I had something on the bottom like x to the negative 2, and then on the top, so as I go to infinity, that would just keep going to 0. As I went to 0, that would keep going to infinity. And then I need something on the top that's just going to be unpleasant, like, oh yeah, here you go. The square root of x to the square root of x to the square root of 1 over x. There you go. So let's do this. So the limit as x goes to infinity of this thing. Right? Now, if I leave it in this form, okay, I'm going to get 0 over 0 forever, right? Because I'm going to wind up here. If I do the square root, if I do this, this is going to wind up being x to the negative 1 over 2, right? And if I don't try to, like, do something about it, I'm going to just keep taking the derivative forever. And the answer is you got to cancel it, right? So you can have things that go off to infinity. You can have things that you just make worse. Okay, so I can't have this thing, right? And the appropriate thing to do here is to cancel and move everything over and be done with it, right? But let's say you didn't do that. You kept taking the derivative. If I took the derivative of this, I would get, the limit as x went to infinity of negative 1/2 x, this goes to 0, this whole bit goes to 0. I would get negative 1/2 x to the negative 3/2 over negative 2x to the negative 3. Right? And then I'm just going the wrong way. Right? See, and then if I took the derivative, and further derivatives are going to make it worse. Okay, so the solution is to step back and do the cancellation. For this one, step back and do a cancellation. Right, you can imagine if this was e to the negative x or something like that. And speaking of that, let's do one of those. So let's say I had e to the negative x over this. Right, now e to the negative x, as I go to infinity, oh, that goes to 1. Nah, forget about that. Put it back to the other one. Sorry about that. We'll just leave that. I'll have to come up with a better example for that. I should have had one on hand. Okay, so I'm running out of time, and I haven't finished yet, and I've still got to do the exponentials. So this video is going to go long. I'm sorry about that. Let's talk about other forms. So so we need to talk about changing products to fit. Okay. So the classic example of this is something like the limit as x goes to 0 plus of x times ln of x. Okay? And you get this situation where you get things like 0 plus times infinity. And that's undefined. I can't do that. Okay? So for this one, I kind of have to fix it. So what I'm going to do is I'm saying 0 plus times infinity is not defined. But I can fix it. Okay, so what I'm going to do is I'm going to fix this to be a quotient. So x, right, x equals 1 over x. Okay, so what I'm going to do is I'm going to move this to the bottom as a 1 over x. So what I'm going to do is I'm going to do the limit as x goes to 0 plus, and instead of having this, I'm going to put ln of x on top and 1 over x on the bottom, right? Because x equals that. 1 to 5, how do we feel about what I just did? That's a little weird. And what I wind up with here, now I've got something, this bit goes to negative infinity, this bit goes to positive infinity. I've got a L'Hopital's rule situation. So what I did was I took this nice pretty product and I stuck one of them on the bottom by making it a fraction. And now I've got something that's L'Hopitalable, so to speak. Right? So now I take the derivative of the top and the derivative of the bottom, and I wind up with 1 over x over, and the derivative of this is x to the negative 1 on the bottom, right? All I did was I shoved this thing to the bottom. Right? It was on top as x to the first, and now I've shoved it down to the bottom. So now I've got negative x to the negative 2 on the bottom. Now, instead of taking, if I tried to take a derivative of this over and over and over again, I'd be in trouble. But what I want to do now is look at this and go, okay, well, that means I want to cancel, right? So what I'm going to do is I'm going to bring the stuff on the bottom to the top and the stuff on the top to the bottom. I'm going to do this. So this x is going to go down there. That x is going to go up there. This is going to be negative x squared over x. And I'm going to do a little canceling. One to 5, how do we feel about that one? All right, this is me futzing around with the product. And I could do the same thing for quotients. Okay, so if I have I could do the same thing for differences. So let's do, that one's on the homework. I don't want to, oh, I did sine of x times ln of x. Same principle. Let's do, which one did I end up doing? X ln of x? Okay. Let's do one of the differences here. Let's do, secant of tan. Yuck. We'll put that there. We'll do the one that I wrote. So let's do, this one's a difference. So let's do this one. The limit, as this is actually one of the homework problems. I don't know. I don't think I posted the homework yet. 1 over e to the x to the minus 1. Now, here what I've got, this is going to be infinity, and this is going to go to infinity. And infinity minus infinity is bad. That's non-determined. I can't, what is infinity minus infinity? So what I'm going to do is I'm going to take a common denominator. And this is going to have some algebra involved. So this is e to the x minus 1 over x times e to the x minus 1 minus, let's leave it there, minus x over x times e to the x minus 1. A little bit of algebra, which is going to equal the limit as x goes to 0 plus of e to the x minus 1 minus x over x times e to the x minus 1. Okay? How do we feel about that 1 to 5? Okay. So now I've got something. This bottom bit is going to go to 0 because that goes to 0. This top bit, this piece is going to go to 1. This piece goes to 0. So this whole bit here goes to 0. So now I can apply L'Hopital's rule. And I do the derivative of this minus 1 minus x over the derivative of this bit. And the remainder is left as an exercised. Well, you do the rest. Okay, I always wanted to write that on a test, right? Because book writers always do that. They go, "This is left as an exercise to the reader." I always wanted to, do in the middle of the homework. This proof is left as an exercise to my reader. Stop it. Okay. Let's do one more. And this one's exponentials. And these are tricky. All right. So I want to do an exponential. And I'm sorry I'm over time. But I am. And you need to see this one. Okay. Now, use the Exp notation. What I'm going to do is I'm going to use... okay. So do exp of ln of whatever is bad. Okay, with a power. So recall the exp and natural log, right? They're inverses of each other. So as long as I'm positive, as long as whatever's bad is positive, I can take the exponential of the natural log of it. And I can also take the log of the exponential of it. Because I haven't done anything. I've gone that way and then back, because they're inverses. Okay, so let's do an example. Do the limit as x goes to 0 from the right of x to the x. Now, look at what's happening here. What is 0 as a base? What is 0 to any power? Okay. Here's the problem. Zero to any power is 0. But any base to 0 is 1. Ugh. Missing a clip. Okay, so how am I going to fix this? So, I watched a Steve Allen. Was it Steve Allen? No, it wasn't Steve Allen. It was somebody. So I don't remember who was the guy. Tim Allen. So there's an old Tim Allen special on I think it's either on Netflix or Amazon Prime this month, which they filmed in Tampa at the Tampa Theater, which is men are pigs, and he's got the grunts, and I thought it was really funny. I should start doing that. I'm gonna steal his shtick. Anyway, this limit as x goes to 0 plus of x to the x, right? What I'm going to do, first of all, x to the x is only defined on positive. So what I'm going to do is I'm going to take the exp of the log of the thing on the inside. How do we feel about that 1 to 5? Now, since exp is continuous, it can come out. And this is why we are using the exp form instead of the e to the thing. Now, I use a little bit of algebra here. No calculus has been done yet, except for, of course, that. But I'm not taking any derivatives here. ln of x to the x equals x times ln of x. Oh. Okay. I can't keep doing that. Now this thing right here is now a product that I'm about to turn into a quotient. I actually just did this bit. Right? This is now, that's x to the minus 1. This now goes off to infinity. That goes off to negative infinity. I'm going to get limit as x goes to 0 of the derivative of the top, 1 over x over negative 1 x to the negative 2 equals exp of the limit as x goes to 0 plus of, okay, so this right here becomes x to the negative 1. I'm going to flip it to the bottom. This is going to be just x on the bottom. This negative 2, that's going to be a negative x squared on the top. That's going to cancel, and that's going to cancel. Bye-bye for you, bye-bye for you. I'm so over time. Okay, so I just do a little canceling, and I get exp of the limit as x goes to 0 plus of negative x, right? And then I do a little direct subbing, and I get exp, oops, I missed my brackets, exp of, I sub this in, and I get the exp of 0, and that equals 1. So how do we feel about that 1 to 5? Oh. A 3. Okay, these are tricky. These exponential ones are tricky. I will try to find some with more videos on the homework when I post the homework, because these are tricky. And if you guys want, I will post some, I can post more example videos if you want, if you guys are having trouble with a particular piece of this. But these are tricky. Okay. So today we went over L'Hopital's rule, and we had this big warning about the fact that I can't mix stuff, right? So make sure you've got either 0 over 0 or something infinite over something infinite. Don't try to mix and match your zeros and infinity. These are two separate things. That is the absolute most common mistake when using L'Hopital's rule, is using it when you shouldn't. And it's very, you're moving through the task, and then all of a sudden there's a change-up pitch, right? Thrown right down the middle. That's something that you should not be doing, you should be doing just or taking a limit of it straight. It might even be something that you can do a direct substitution on, right? It's just it's an easy one that's hard because you're not expecting it, right? It's a change up pitch. And the other thing is, remember, you're taking the derivative of the top and the derivative of the bottom separately. And all these things are just fancy ways of making things work with L'Hopital's rule. So if you've got something that you got something that's got a weird form, see if you can make it into something that's a quotient. Okay, so that's it for tonight. Next time, what is next time? I don't even know. Next time we are doing derivatives in the shapes of graphs. So the thing that we've been starting on, the thing that we've been talking about in class already, we're going to actually do that. And then we've got optimization coming up. So I'll probably do optimization 1 first. So next time will likely be optimization 1. And then we'll do derivatives of the shapes of graphs. And then we'll do more optimization problems. Yeah. Any questions? Yeah, people want example videos, I know. As I said, I'm not sure if we're going to do derivatives and shapes of graphs because I've been kind of pounding that on the other stuff. Okay, so what I'm going to do is I'm going to stop Twitch. I will hang out for the next 5 minutes. If you want 5 to 10 minutes, if you want to ask questions in Discord.